In this video, I am going to talk about the shift register counters. What are the shift register counters? Unlike a counter, it has no specified sequence of states. These are actually the special types of shift registers in which we are going to see a specified sequence of states. That is why these are known as shift register counters. Now, what is going to happen in the case of shift register counters? The output will be fed back again as the input to the first flip-flop. So, depending upon the nature of the feedback, there are two types of shift register counters. First is the ring counter and the second is Johnson counter. First of all, I am going to start with the ring counter. Ring counter is also known as circulating register. So I'm going to start the explanation of ring counter with the help of example of 4-bit ring counter. In 4-bit ring counter, we are going to use 4 D flip-flops. The same, first of all, clock signal has been given to all the flip-flops as we have already done in the case of shift registers. D, Q0. Q0 will be given as the input to flip-flop number 1. Q1 will be given as the input to flip-flop number 2 and Q2 will be given as input to flip-flop number 3. Now, what about the feedback circuit? Now, you can see it over here. Q3 is given back again as the input to the first flip-flop. So, this is the connection of the feedback circuit in ring counter. In the same manner, you can design 5-bit, 6-bit, 10-bit, 20-bit ring counter. You just need to pick the same number of D flip-flops together and connect the feedback. The feedback will be the output of the last flip-flop will be connected as the input to the first flip-flop. We can also use JK flip-flop for the implementation of ring counter. The only difference will be the output from the last flip-flop will be given as the input to J as well as K to flip-flop number 0. So that will again start behaving as a ring counter. Now, to start with the explanation, initially what we are going to do, initially we will design that the input to flip-flop number 0 is 1, whereas the output of all the flip-flops are reset. So that means when clock is 0, we have given first input to D and all the outputs of the remaining flip-flops are reset. So as per the truth table, when clock pulse is 0, as D is 1 for flip-flop number 0, Q0 will also become equal to 1, whereas the output of the remaining flip-flops is equal to 0. Now what will happen when the first clock cycle will appear? When the first clock cycle will appear, this 0, that is Q3, will be given as the input to this D. So now flip-flop number 0 input D will become equal to 0. On the other hand, Q0 is connected with D. So 1 will transmit over here. Now D will become equal to 1. So if input D is 1, output will be 1. Just a reminder, what is D flip-flop? D flip-flop is nothing but a delay flip-flop. If input is 0, output is 0. If input is 1, output is 1. So for the first clock cycle, we will have the outputs. You can see now the output of first flip-flop, that is flip-flop 0 is 0, 1, 0, 0. For the second clock cycle, you can just see it over here that now this 1 is actually going to be transmitted one by one to the next flip-flop. So for the second clock cycle, Q2 will become equal to 1 and the third clock cycle, Q3 will become equal to 1. So this is how your flip-flop is going to work in ring counter. So you can see the explanation. Initially we have 1000. That means flip-flop number 0 is set to logic 1, whereas the others are at logic 0. So one by one, this 1 will be transmitted to the next and next outputs of the flip-flops. That is why it is known as circulating register, because it is just circulating the event to the next flip-flop. So this is the counting table. The last is the timing diagram. So in this case, first of all, when we have clock is 0, so you can see it over here, Q0 is 1, remaining all the outputs are 0. So you can see Q0 is 1, remaining all the outputs are 0. For the first clock cycle, we have 0, 1, 0, 0. So for the first clock cycle, we have 0, 1, 0 and 0. In the same manner, you can just draw the timing diagram for the remaining clock pulses as well. Next is the Johnson counter. So what is Johnson counter? In Johnson counter, you can see the feedback. Now, the complement of the output of the last flip-flop, that is Q3 bar, if I talk about a 4-bit Johnson counter, Q3 bar will be given as the input to flip-flop number 0. So this is the feedback circuit in the case of Johnson counter. If I talk about the function of Johnson counter with the help of JK flip-flop, in JK flip-flop, if I'm going to use JK flip-flop over here instead of D flip-flop, Q3 bar will be connected with J, whereas Q3 will be connected to K. So these are going to be the connections for 4-bit Johnson counter. Now, there is a very important point in the case of Johnson counter is modulus. So, what is the modulus of a Johnson counter? It is 2n, where n is the number of stages in the counter. For example, if we have 4-bit Johnson counter, so it is going to have the modulus of total 8, that is 0 to 7. So 2 into 4 is 8, 8 means 0 to 7. Let us talk about the working of this 4-bit Johnson counter. Now, the initial condition will remain 0, 0, 0 and 0. That means initially all the 4 outputs are 0, 0, 0, 0. If Q3 is 0, definitely Q3 bar will become equal to 1. So 1 will be given over here. So you can see, first of all, when clock is 0, all the 4 outputs are 0, 0, 0, 0. Now for the first clock cycle, this 1 will be given as the input to flip-flop number 1, flip-flop number 0. So if D is 1, Q0 will become equal to 1. So you can see, for the first clock cycle, Q0 will become equal to 1. On the other hand, the remaining outputs will remain equal to 0, because 0 input, 0 output, 0 input, 0 output. For the second clock cycle, still Q3 is 0, so Q3 bar will become equal to 1. So once again, 1, and now this 1 has been transmitted further to the next flip-flop. So input 1, output 1. Now once again input is 1 and output is 1. So you can see, we are just adding ones in the truth table, the counting table of this Johnson counter, till the point all the outputs are 1, 1, 1, 1. Now if Q3 becomes equal to 1, Q3 bar will become equal to 0. So now 0 will start transmitting as the input to flip-flop number 0 through flip-flop 1, flip-flop 2 and then flip-flop 3. So now you can see it over here, 0 here, then 0, 0, because still Q3 is 1, so Q3 bar will be 0. Then we have 0, 0, 0, 1. So we have the modulus of 8 in the case of 4-bit Johnson counter. That is why it is also known as shift counter. So the last is the timing diagram. So the timing diagram is nothing but with the help of this truth table over here. When clock is 0, all the 4 outputs are 0, 0, 0 and 0. For the first clock cycle, Q0 is 1, remaining all the 3 outputs are 0, 0, 0, 0. So this is 1, 0, 0, 0. Then we have 1, 1, 0, 0. Then we have 1, 1, 1, 0. Then we have 1, 1, 1, 1. Now afterwards, 0 will be added over here. So 0, 1, 1, 1, 0, 0, 1, 1, 0, 0, 1. You can see, you can refer it over here as well. and then we have 0 0 0 0, that is the last value.